In the last video, we took a look at a type of series that we called a telescoping series. And in this video, we're going to start to take a look at the idea of what we call a geometric series. And in fact, this is going to be a very common theme that we're going to have throughout this section and the remaining sections in Chapter 5, is that we're going to be talking about lots of different kinds of series or addition problems. So let's see what we have here with a geometric series. We'll give a series this particular title if it is of the following form. So it has to be in a form that is equivalent to something like this. So I'm going to imagine that I have I starting at 1, going to infinity, and the shape of every geometric series is going to look something like this. Now, A and R here are going to represent numbers. This could be something like 2 times 3 to a power I minus 1. Notice the only variable that's actually going to be in here is this value of I. A and R again are replaced by numbers. But if I have something of this sort of a shape, I will call this a geometric series. Now, it's important to note that I here does not necessarily have to start at 1, and my power, my exponent up here, does not always have to be I minus 1. Rather, I need to have the following happen when I plug in my first possible value of I. Notice here, when I plug in this value of 1 for I get an exponent of 0. And so it's totally possible to re-express a geometric series with, say, a 0, and then make this a times r to the power I. I could have this starting at the number 12 and have a times r to the I minus 12. I just need to make sure that when I plug in that first value of I, my exponent turns into 0. Now, what that's going to allow us to create is the following addition problem every single time. Notice if I have r to the 0th power, that's going to get me a 1, multiplied by a gets me a. If I increase I to a 2, I'm going to get a times r to the first power. If I increase I again, I'm going to get a times r to the second power. And then I'll get a times r to the third, and so on and so forth. So I can see here that this geometric series has this kind of shape, a times r to a power that begins at 0, and it looks like this addition of values. Now we're going to add a little bit more to this description here. First off, we're going to make it the case that a is not the number 0. Notice that if a was the number 0, this addition problem becomes incredibly boring, and so we're not really interested in dealing with that. In addition to this, we'll see that a always exists as the first item in this addition problem. And we can also see that the value r is called the common ratio because it is an item or the value that I multiply each individual term by to get to the next term, right? Notice if I take a, multiply by an r, I get over here, multiply this by r, I move over here, and so on and so forth. Okay? So we've actually already seen examples of geometric series in the videos for this section thus far. We've already talked about a series that looked like this. We had, this was back in, I believe, example number 2. And it's actually a geometric series. I can easily see how I could get there by just trying to reshape the interior of this series to look more like number times number to a power of I minus 1. Notice that that's really easy to do here. If I imagine that I kind of have like a stack of 1/2s here, I have I of them on the stack, and if I just peeled one of them off, I would have one less on the stack. But now I can see the components from up above. I have an A and I have an R, and they're being multiplied together. R is being raised to the power of a I minus 1, which is going to start at a power value of 0. So this here is a geometric series. Now our goal is going to be to try to understand why we care about geometric series and how exactly can I understand their behavior. Of course, like we saw in the last couple videos, finding our green S sub n is going to be very, very important. Let's take a look at the next page, the theorem that goes with geometric series. So I'll state this. The geometric series a times r to the I minus 1, I starting at 1 and going to infinity, we know that that particular series is going to be one of two things. Obviously, it's going to be convergent, or it could be divergent. The question is, when will it be each? Well, surprisingly, this actually all comes down to looking at this value of r. If it's the case that when I take r and absolute value it, if I get a number that's less than 1, then the series converges. And even more than that, I can actually state that the series itself adds up precisely to the following value, a over 1 minus r. Okay, that's kind of strange. So if r has this property, I know that the series is convergent, and more than that, I know it adds up to exactly this fraction. The series will also be divergent if I find that the absolute value of r is greater than or equal to 1. That is, essentially, if r is any other value. Now, this is a pretty bold claim, and most of the theorems that we're going to be seeing in this class we will attempt to prove. In mathematics, you would have to prove all the statements that you make, right? We don't get away with just like stating things and just going, well, I don't know, it kind of works this way. You have to defend your position. You have to make an argument, as we've done with many of the different ideas that we've seen so far this semester. So we're going to go ahead and attempt to actually justify this here. So let's see how we would go ahead and do this. I'm going to break this up into some different cases. I'm going to look at some different values of r and see if I can make some determinations about our green S sub n sequence that we could form, and then see if I can confirm whether or not the series converges or diverges at these different values. So let's start here with r equaling 1. Okay, let's just see what happens if r was the value of 1. So I'll say here that in this case, notice that we would have a series that would look like a times 1 to the I minus 1. So then it would be pretty easy to go ahead and start to write out the partial sums of our series. So let's see. I can say here, in this case, we would have a times r to the I minus 1. That would be equal to really just a times 1 to the I minus 1. So our series here would just look like a plus a plus a, on and on and on for the rest of time. And so we could easily go ahead and start to see that S sub n would be adding up the first n items. So that would be a plus a plus a, and we would go on and on and on. We do this a total of n times. Well, of course, that makes it really easy to come up with a formula for this, because if I add a to itself n times, I just get n times a. Well, that's amazing, because I have a green formula, which means I can take a limit of it, and I'll be good to go. So I'll see here that if I do a limit as n approaches infinity of S sub m, I know that as n gets large, if a is positive, I'm going to be getting positive infinity. If a is negative, I'm going to be getting negative infinity. So I'll say here that this is equal to plus or minus infinity. I'm not sure which one. It depends on a. And so we can say that S sub n diverges, which means that the series diverges. Okay, so we've covered, in the case when r is 1, the geometric series diverges. We have a little argument here to explain it. Notice that's just one of the possible values of r, and it does fit with this second bullet point down here. Well, we've covered one r, but we only have infinitely many more to go, so buckle up. All right, well, let's suppose now something else. What if we looked at r not being the value of 1, right? Like maybe r is something else. Well, in this case, let's see what we come up with. So I'll state this. in this case, we can say that our a times r to the I minus 1, well, can't really be simplified too much. Now, I can go ahead and think about writing it out as, again, a plus a times r plus a times r squared plus a times r cubed, and like on and on and on. But that doesn't really help me. And if I wanted to write out my s sub n, I could do that, but that doesn't really help me that much either. Notice, I could state that s sub n is going to be equal to a plus ar plus ar squared plus ar cubed, and I could keep going and going until I get to ar. Notice if I plug in n, I would get power n minus 1. Well, it's true. Again, it's not a nice formula. It's not like n times a. It's not easy to write. But it's actually something that I could work with slightly. Take a look at this. This is a really clever move. What if I took that s sub n, right, that entire same exact line that I had up above, but what if I took both sides of my equal sign and I multiplied by a value of r? Let's just see what would happen with that, okay? So notice that would mean that the power on all of these r's would just go up by 1. Now, when I multiply this a by r, I'm going to get a times r. I'm going to actually shift it over. I'm going to leave a little blank space right here. Notice multiplying r by this ar is going to get me the ar squared. And then I'll obviously get an ar cubed. And then I'll go all the way up to an ar n minus 1. But notice, when I multiply r to this term, when the power goes up, I would have one extra piece. Notice that I have just one extra item in here. At least it looks like there's one extra item. If I bumped everything back a position, I have the same number of items. Just multiplied everything by an r. Now, why do this? This seems like a strange move. Well, if you take a look really quickly, you'll see that a lot of the items in the first equation match the second equation. So my plan is going to be to subtract them. Now, on the left-hand side, that doesn't really allow me to do too much. I essentially can have that I'm going to have s sub n minus r times an s sub n. But on the other side, I'm going to get some really convenient stuff. Notice that I'm going to get like ar minus ar. That's going to cancel. My ar squareds are canceling, my ar cubes are canceling, my ar n minus 1s are canceling, and all I'm going to be left with is a minus my ar to the n. Notice that by doing this, I was able to get rid of the dot 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 that existed here. And so maybe I can ultimately find a green formula for my s sub n. Well, let's take a look. I'm going to go ahead and on the left side here, I'm going to factor my green s sub n out. On the other side, I'm going to factor out a value of a. And notice then I can solve for my s sub n by simply dividing that set of parentheses over to the other side. So I end up with this. Now this right here is great news. I have a formula for s sub n, which means if I can take its limit, I'll know what the series converges to, or if it doesn't converge. Now I'm going to go ahead and start to break this up into some smaller subcases just to kind of see what happens when I try to compute a limit of this thing. So let's see what we have. Let's suppose that it's the case that the absolute value of r is greater than 1, or that maybe r itself is equal to negative 1. Notice that both of these would be cases that would be a part of this divergent group. So let's see if we can actually confirm that the series would be divergent. Well, if this is the case, then what we have is we would calculate a limit as n approaches infinity of s sub n. That, of course, would be a limit as n approaches infinity of a times 1 minus r to the n over 1 minus r. Now, if I think back on my properties of limits here, I'll recognize again that if a and r are constants and n's the only variable here, I can simplify this down a lot. Notice I would do a limit of the top and a limit of the bottom. But if the limit of the bottom is, if the bottom down here is just a number, then the limit of it is just the same thing. So I can easily state that I'm just going to end up with a 1 minus r in the denominator. When I do the limit of the top, notice I have something times something, so I can do the limit of each piece. But a limit of a, well, that's just a. Then I can do the limit of the subtraction. But when I do the limit of the subtraction, I do the limit of the first piece, which is just going to be 1, and then I would be left with calculating the limit of this second piece. And it's here where something really interesting happens. Do you remember back in 5.1.1, that very first section of chapter 5, the very last theorem even in that section, talked about finding the limit of an r to the n. In fact, I'm going to ask you to go right now, pause the video, go back, look at your notes from that particular section. The very last theorem in 5.1.1 should have talked about what we do when we do a limit of r to a power of n. And see what happens if the absolute value of r is greater than 1 or if r was negative 1. Pause the video, go take a look. Well, if you went and you looked at the video, what you should have seen is that definitely we know that this thing here is not going to exist, right? That means we might have something like a positive or a negative infinity, but we got this is divergent. So I'll state here that by 5.1.1, we know that the limit of r to the n as n approaches infinity with these values of r is divergent. And so the limit as n approaches infinity of s sub n is divergent, which implies the series is divergent. So look at that. If r was the value of positive 1, negative 1, or its absolute value was greater than 1, we ended up with divergent, just like the theorem said. Now, of course, we have one more case to consider, which would be what would happen if the absolute value of r was less than 1? Well, again, we can take a look at a lot of the same pieces here. We're still wanting to compute the limit as n approaches infinity of our green s sub n. This is obviously going to lead us to the exact same point as we had before. 1 minus our limit as n approaches infinity of r to the n over 1 minus r. So in this case, if r is less than 1, then, again, by looking back at those notes in 5.1.1, we know that the limit as n approaches infinity of r to the n in this case equals 0. And so the limit as n approaches infinity of s sub n is going to be equal to a times 1 minus 0 over 1 minus r, which, if you simplify that up, is just a over 1 minus r. So the series converges because s sub n converges. So I can say thus, our series, which was a times r to the I minus 1, converges, and remember, it's got to be equal to whatever we found for the limit of our green s sub n, which means that we have the sum of the series is a over 1 minus r. And that's exactly the formula we had here in this box. This is an awesome justification of this particular theorem, and it shows how all the classifications of these values of r can be justified. It also shows where this cool formula comes from. And these are going to be really important ideas to remember as we continue to look at some examples in the next videos.